In this video, we're going to talk about the difference between transverse and longitudinal waves. But first, let's talk about features common to both transverse and longitudinal waves, and any wave in general. One is that a wave is a traveling disturbance, which means that at some point a force was applied and causes the disturbance to then move through the medium. The second is that a wave carries energy, not matter. So any wave, whether it's light, sound, water, any wave carries energy, not matter. So the matter is simply going to oscillate back and forth in whichever direction is required. Two categories of waves. One is direction-based, that's what we're going to talk about today. And the other is medium-based, which will be in another video. So the first one, direction-based, is talking about transverse waves where the oscillations are perpendicular to the direction in which it moves. So for example, if a wave is moving left to right, then the oscillation will be up and down, forming a right angle, hence perpendicular. In our little drawing here, we have the direction of the wave going to the right, and our little guy is moving the oscillation up and down, creating this nice pulse that we see. So here is an animation that shows a transverse wave where you can see that the particles are definitely going up and down as the wave is traveling left to right. So the wave is going from left to right, but the oscillation is up and down, forming that right angle. Now, here's where we are talking about carrying energy, not matter. If you keep an eye on one dot, you will notice that the dot does not travel left and right. It simply moves up and down. Another way to think about it, think about the wave in any sporting event. The people are not moving in the stadium around the sides. Instead, they're simply going up and down in their current seats, but you can definitely see the wave traveling in the stadium. Some terminology for a transverse wave: crests and troughs. So a crest is a high point, troughs are low points. So in a wave, you will see, here's our outline of the wave. You'll see the crest is the top and the trough is the bottom. The next type of wave is the longitudinal wave, and in a longitudinal wave the oscillations are in the same direction as the motion, or parallel. In other words, if you have a wave that is moving from left to right, the oscillation is going left and right, so in the same direction. In our little diagram here, we have our wave again going from left to right, and our little guy is pushing the oscillation left and right. And you can watch the pulse travel down the spring. So again, here's a little animation that shows a longitudinal wave where you can definitely see that yes, the wave is traveling from left to right, but the oscillations are now going left to right as well. Also, check out a dot. You'll see that that dot is no longer moving up and down, but is moving left to right, and is not traveling with the wave. Again, emphasizing that waves carry energy, not matter. The matter simply moves back and forth and back and forth. So some terminology for longitudinal waves are rarefactions and compressions. The first one, which is pretty easy, are compressions. It's where the air or other medium is compressed together. That would be right here. All the lines are very, very close together. They're compressed. And rarefactions are basically the area in between. So here is between the compressions, showing a less dense area, lower pressure, and where it's more stretched out.